blow out. Newton's laws of cooling, not motion, are at work here. One of these laws says that the larger the difference between the temperature of a hot substance and its surroundings, the more rapidly it cools down. This is why, for example, our tea cools quicker in winter. Also, when we blow over hot tea or milk tea to cool it quicker, we replace the hot air that accumulates over it by cooler air, and this helps more rapid cooling. There is another law of Newton which says that the larger the surface area of a hot substance, the more rapidly it cools. This is why pouring tea into a saucer helps to cool faster. Both these laws operate in the case of the candle and cool the burning wax vapor below its ignition point. Ignition point is the temperature below which wax vapor does not burn. When we blow air at the candle flame, we replace the hot air surrounding the flame by cooler air and distort the spherical shape of the burning wax vapor, not the flame, which is not spherical, and increase its surface area. Simple geometry shows that for a given volume of the substance, the spherical shape has at the least surface area. Any distortion from the spherical shape therefore increases the surface area of the substance and helps cooling. Taking advantage of this latter feature, contrary to what you might expect, it is even possible to ignite coal or strip off paint by a jet of sufficiently hot air. Such contraptions, called hot air strippers or pokers, are now commercially available.
Einstein in your thinking. The explanation mentioned by Schrödinger was discussed by Einstein in an article reprinted in Einstein, a Centenary volume. The rotation of the liquid causes a centrifugal force to act on it. This, in itself, would give rise to a change in the flow of the liquid if the latter rotated like a solid body. But, in the neighborhood of the walls of the cup, the liquid is restrained by friction, so that the angular velocity with which it rotates is less than in other places near the center. In particular, the angular velocity of rotation, and therefore the centrifugal force, will be smaller near the bottom than higher up. The result of this will be a circular movement of the liquid of the type which goes in increasing until, under the influence of ground friction, it becomes stationary. The crucial point here is that the differences in angular velocity within the rotating liquid arising from viscosity result in pressure differences, or so-called Bernoulli's principle. A pressure gradient develops along horizontal planes with the pressure increasing gradually outward. The velocity is the least along the walls of the cup due to friction. In addition, a vertical pressure gradient also develops between the top and bottom layers because of friction with the bottom of the cup. slowing down the tea at the bottom compared to the top. These two pressure gradients set up what is known in hydrodynamics as the secondary flow within the liquid. While the tea is rotated, its surface becomes curved and the direction of the secondary flow is such that the tea leaves are driven away from the center. If you observe carefully, you will see that the tea leaves have a tendency to stay away from the center. Once you withdraw the spoon and let the tea leaves settle down, its surface begins to flatten out. The liquid mass readjusts itself and the pressure gradients decrease. This results in a reversal of the direction of the secondary flow, bringing the tea leaves to the center of the bottom.
Weigh yourself. When you bend forward, the muscles that help you do that pull up the lower half of your body. This is why your body exerts a lower pressure on the weighing machine. When you lift out an arm, the muscles to do this push down on your shoulder and increase the pressure on the weighing machine. Of course, your mass did not change at all. It is the Newton's third law of motion that operates. The sudden motion, or strictly speaking, the momentum of your hand upward must be balanced by an opposite movement downward.
It is atmospheric pressure in conjunction with Bernoulli's principle that makes a liquid stick and run down the side of the container. The Bernoulli principle is a very general principle of fluid flow and has numerous applications. This principle is really a consequence of the fact that energy can neither be created nor destroyed. This is the fundamental principle of the conservation of energy. Imagine spectators crowding in the foyer of a cinema hall after a show. If you're in the foyer, you feel everyone pressing against you, and you move slowly towards the exit. When you come close to the exit, however, you start moving quicker since the pressure on you drops. This is because pressure is generated by the sideways pushes of people around you. When everyone moves forward, this pressure drops. The same is true of the molecules of a liquid. When they move slowly, they jostle and collide against one another and the walls of the container, creating a pressure. When they approach a narrow section of the tube, they move forward faster because, being incompressible, the same amount of fluid has to pass through the narrower sections in the same time. The pressure consequently drops. When you pour a liquid out of a thin-walled container, the bottom layer of the stream in contact with the edge of the container turns around much faster than the top layer. According to the Bernoulli principle, therefore, there is a pressure drop across the width of the stream, and the atmosphere presses the stream against the container side. If you pour out the liquid fast by turning the can quickly, the stream acquires an overall velocity. There is no longer any appreciable pressure drop across its width, and the liquid does not stick. In order to prevent this sticking of liquid, juice bottles usually have a thick ground skirt at the mouth, which eliminates the difference between the curvatures of the bottom and top layers. Juice bottles usually have a thick round skirt at the mouth, which eliminates the difference between the curvatures of the bottom and top layers of the flowing liquid. There is therefore no pressure drop across it. Milk and teapots have a spout or lip which makes the stream run down it and drop straight into the cup without sticking.
It is indeed amazing that
A simple everyday occurrence contains
Such rich and complex
Scientific principles and mathematical concepts.
preview.
Model part, model.
such